Okay, hi everybody. My name is David Targan, and I am the director of Loud Observatory. I had been a student at Brown in 1974 when I came to study physics and astronomy, and I first entered that observatory within the first week, definitely, of school, and ever since then I've just been just completely in love with the place. And I was fortunate enough, after being away for 10 years, to pursue my PhD and get tenured in Minnesota to get a job back in the physics department that included being the director of this observatory. And so it's been great, a tremendously exciting 28 years or so. And during that time, we've done a lot of things. Originally, the observatory, when I came back, was somewhat better than when I left it, but I think over the 28 years, we've made some improvements, some definitely positive strides. The biggest one being a major renovation that occurred with the help of funds from private donors and as well, and also funds from the university's deferred maintenance budget, because there was a building on our property that was a rental property, and we found out that that was not up to code, and it turned out that we had to, Brown chose that it was, to destroy it, and the money that was that they were saving to go into the restoration of that building ended up being used in the creation of the front lawn and part of the elevator, the new elevator that was created to become ADA compliant. The restoration itself was done in a way that was consistent with the original construction of the building. So, for example, the rock, that granite that was used in the bottom of the observatory, they went back to the same quarry to get the same kind of rock more than 100 years later. In 1991, we had our 100th anniversary, and we had several hundred people at the 100th anniversary of the observatory. We couldn't really do that today because basically Rhode Island has probably justifiably among the best fire code laws in the country, and we're very observant. In fact, I'm surprised that when I got up here, the automatic announcement that usually I hear in this room about the exits and everything, but you know where the exits are. So, but it is in fact one of the reasons why we could not have an all-out bash at the observatory on today, the exactly 125th anniversary of the building, and that is that we really could only hold maybe 100 people maximum in the building, and maybe 20 or 25 people in on the first floor area where we have our little lecture hall. So anyway, I'm glad everybody is here to join us in this celebration, whether you're friends of LAD or parents for family weekend. I welcome you here, and it's my pleasure to introduce one of our most skilled and knowledgeable astronomers and all around just experts in all the machining and all the equipment that we have, as well as the history, Mike Umbert. Thank you.
So as you might expect, an observatory like LAD was primarily used for teaching students, and we've always opened the building to the public to look through the telescope. But one of the things that I'll be talking about today is one of the things that you might not know too much about, which is timekeeping. The process of setting clocks involves making astronomical observations, and throughout history, astronomers have been the ones who are tasked with making these measurements and keeping the clocks reliably running so that they're accurate and on time. I've got an illustration here which very literally has the title of my talk in it, From Star to Clock. Here we see an astronomer in an observing chair looking through a transit telescope. Behind is a clock. And if you look very closely, you'll see something odd. There's what appears to be a tube connected from the side of the clock to the hat that he's wearing. The book that I scanned this from makes absolutely no mention of what that is, but I have a pretty good idea. Imagine astronomers who are working in the dark. You want your eyes to adapt to the dark so that you can be as sensitive as possible to very dim stars that you're looking at through the telescope, so you don't want to have a light on. Typically, you would have a lantern with a flame, and we're not allowed to do that anymore. Then you have a shutter, which you can use to close the lantern, and an astronomer might walk over to the clock, lift the shutter up just a little bit to shine some light on the dial, read the time, and then start counting in your head, listening to the ticks which are conducted through this tube to his ear in the side of his hat. And this would allow him to look through the telescope, and at the exact moment that you see something interesting happen, you would note what fraction of a second between the ticks that you're counting the event occurred. And typically a trained astronomer could get down to about 1/10 of a second with this, or even a little bit better. Our story begins with, quite literally, a train wreck. This is the Providence and Worcester Railroad. In the 1850s, the railroads were growing so quickly that they were having difficulty managing this. Between Providence and Worcester, they had only been able to lay down a single set of railroad tracks between the two cities. So you might wonder, well, what happens if you have a northbound and a southbound train on the same track? They would have these spurs where the train would pull over to the side, the one that's heading north, look at your wristwatch, your pocket watch, wait for the time when the southbound train is going to pass you, then get back onto the main track and continue on. It didn't work all the time. This particular image that you're seeing is one of the very first photographs, the daguerreotype of a train wreck, and that occurred in Valley Falls, Rhode Island. That was in 1853. As you can expect, this made the news, and it wasn't just a single train wreck. There were many of them that were occurring during these decades. The language used here in the New York Times: disagreeable necessity obliges us to shock the sensibilities of our readers by the recital of another terrible calamity from a collision of railway trains. If you look down at the bottom, there's a very telling bit. It says the latter train was, quote, out of time. In other words, they hadn't synchronized their watches properly, and so that they were on the tracks at the same moment. If you've ever seen an old black and white movie, you may have seen a train conductor who pulls a pocket watch out and looks at it. And this is sort of stereotypical. You see it in just about any movie. And this was not just some sort of an idle thing that they did. It was a rigorous procedure instituted by the railroad companies so that their employees would keep the trains running on time, not so much because of the convenience of passengers, but to prevent accidents. There were so many of these accidents, the government threatened to intervene, regulate the industry. They, of course, would not like to have so much regulation, much like today. And what they would do is come up with their own system, industry standards. One of them is standard time zones, like Eastern, Central, Mountain, Pacific. At one time, just about every city would have its own time zone based on whatever the local sundial time was. And so this is the setting for the decades before Ladd Observatory was built. The railroads went to the astronomers and said, we need precise time. A system was come up with where observatory time was transmitted by wire to the railroad offices, and the personnel that operated the trains would then go into the station, compare their pocket watch to one of these synchronized clocks, and then let the engineer know what time it was to leave the station. Throughout the country, we would have observatories, and each one would be serving time to the local community. It wasn't done nationwide. And so this brings us up to the time when Ladd Observatory opened. Here we see an astronomer operating the main telescope. This is the one that's used for general purpose scientific work and for teaching and for public viewing. We still use it today. One thing I should point out, if you haven't been to the observatory, is that when you look at these photographs, I could take a photo today with my camera, upload it to Instagram, and make it look kind of grainy and old, and it would look identical to this. Very little has actually changed. Up on the left, you see the main dome, which is where the telescope that I just showed you is located. But for tonight, I'll be talking about this area here on the right, which is called the Transit Observing Room. That's where the timekeeping activity occurred. So how do we get from star to clock? Here's a blueprint showing the first floor. One thing you'll notice is that the building is perfectly aligned with the compass points, as observatories always are. Here on the west end, we have the transit room. Down in the central corridor is where some of the timekeeping telegraph equipment was located. And then at the very east end, inside this pillar, which is where the main telescope sits on top of, that's where the most precise clocks are kept. So I'll be walking you sort of down the hall here from where the telescope observing station is to where the clocks are. Here's a view in the central hallway looking towards the transit telescope, which is down at the end of the hall. This building was constructed before the neighborhood had electricity, and so you'll notice that there are gas lamps that were used to light it. I said we had a telegraph system, but no electricity coming from the street. We used batteries for that. And you can see on the table, just on the right, over here, that there are some devices next to the control panel for the telegraph system. And here's a view looking in the other direction, standing from the same location. And you can see one of the clock dials here inside this room that we call a clock vault. The clocks are expensive, but that's not why we put them in a vault. That entire pier structure that you see underneath the main telescope is a freestanding structure. In the photos where the building is being constructed, you can see the pier there, and they built the building around it. There are a couple of reasons for doing this. One of them is vibrations. You don't want heavy equipment rolling around on the floor, shaking the telescope and disturbing a sensitive photograph that you're taking. The other thing is we can hollow out the center of the pier and put the clocks inside of it. There's double doors that can be sealed and keep out the drafts. This keeps the temperature inside the vault as constant as possible, because if the temperature changes, the length of the pendulum will thermally expand or contract a little bit. And even just 1/1000th of an inch can throw the clock off by as much as a second a day. And so by keeping them in this stable environment, we protect them from these changes. So we'll start with the telescope. This is the first telescope, transit telescope, that was installed at LAD. The astronomer, Professor Winslow Upton, who was the first director of the observatory, wasn't too pleased with its performance, complained to the factory, and they sent it back to have it repaired. And in the meantime, they used an auxiliary transit shed. This one is located just a little bit to the north of the observatory on Observatory Ave. This building was probably constructed sometime in the 1890s, and it was destroyed about 1920. This may not look like your classic observatory. It doesn't have a dome, but it does have a roll-off roof, so the two parts of the roof slide apart, opens up the telescope to the sky, and here we see an astronomer preparing to make an observation. Despite the fact that this structure is no longer on our property, we're going to go looking for it. I've been working with Peter Van Dommelen, who's a professor of archaeology here at Brown, and last week we had this device. It's called ground-penetrating radar, and we ran it back and forth across our lawn, and we got some anomalies, some signatures. Some of it is probably some buried pieces of metal, perhaps some rebar from a foundation. We also found some places where the walls used to be. So hopefully he'll be bringing his class back a year from now to excavate the property, and we'll see if there's anything buried in the soil. Eventually, the transit telescope was finished. The thing about a transit telescope, unlike the main one that you saw at the beginning, this one can only move in one direction, which is along the north and south line. It can't tilt to look east or west. So through south to the point overhead, which is called the zenith, and then into the north, we can rotate the telescope. And you might wonder, how do we aim at a star? Well, we don't. We wait for the Earth's rotation to cause a star that's rising to move through the view of the telescope, and then we note the exact time when that event occurs. When we look at a star chart here, we see two sets of coordinates, much like on a globe, latitude and longitude. The one that goes up and down, 0 to 60, that's degrees from the celestial equator. So if you can imagine somebody sitting at the equator looking straight up, they're going to see one of the stars that's along that 0 line. Here at Providence, we're up at 42 degrees, and you would see one of those overhead. The top scale is not in degrees, though. It's in hours, and it runs from 14 to 24. So if you look at a bright star like Vega in the constellation Lyra, that one is about 18 and a half hours, and then 2 hours later, you would see Deneb here in the constellation Cygnus moving through the view of the telescope. And so, depending on which of these stars you can see, if I see that one, I know it's this time. If I see a star over here, I know the time is this. One little complication, though, and there are two kinds of time that astronomers use. The first is called sidereal, or star time, and the second is solar, or civil time, the kind of time that you use on your wristwatch. The reason that there's a difference between the two is that not only is the Earth rotating with respect to the stars and the sun, but it's also moving in its orbit around the sun. And so after 23 hours, 56 minutes, and 4 seconds, the Earth will have moved slightly in its orbit and turned enough so that a star is seen in the exact same spot in the sky. But you have to wait almost another 4 minutes for the Earth to rotate just a little bit more before you see the sun in the right sky, in the same part of the sky. So these are two different time systems. One is the 24 hours that we use. The other is 23 hours, 56 minutes. And astronomers have to convert between these two. When you're actually looking through the telescope, you see these cross threads. At the left is a bright star, and the planet Venus is on the right in a crescent phase. There are 5 vertical lines and 1 horizontal. Now, these need to be as thin as possible. And the reason for that is that when you look through a telescope at high magnification, what you see is a pinpoint, like a mathematical pinpoint. And if the threads had any measurable thickness, that would block out the brightness of the star for too long, and it would make it hard to get precise timing. During this age, the only materials that were that thin were spiderweb threads. Now, you might wonder, how do you put a spiderweb thread inside of a telescope? There's actually 2 kinds of threads that spiders make. First, you have the circular ones, which are not very strong, but they're very sticky, and that's what the insect gets caught up in. But then you have the ones that radiate out like bicycle spokes. These are very strong, but not sticky. So, and I've done this. What you do is you have a jar where you keep your spiders, and you feed them these flightless fruit flies, keep them alive, and you reach inside with a pencil, and you scoop up the spider, and over a table, you push it off, and as the spider falls, you turn the pencil slowly to wind the spiderweb threads around the pencil, and then you can harvest those. Inside the telescope, there are slight grooves that are placed there by a very precise machine to keep those lines exactly at the right distance apart, and you use those as guides to place the spiderweb threads inside. When looking through the telescope, you would then tap a telegraph key each time the star passed one of these 5 lines. So you'd line it up so it's along the horizontal and wait for the star to slowly drift because of the Earth's rotation past 1, 2, 3, 4, 5, and take the average to get the center, the time that it crossed the center line. This is the control panel for the telegraph system, which has relays. Here in a modern building on campus, we have Ethernet and Wi-Fi all over the place. That observatory is wired to the hilt with telegraph wires. They run from the telescopes through the basement, up to the dome, down to the library, and all over the place. And they still work. I've run telegraph signals through them. At this master control panel, you can decide which clock you want to examine. So it might be one of the ones in the clock vault that I was talking about. Could be a portable clock. One of these box chronometers, they call them. These are the kinds of timepieces that are used by ship's captains at sea for celestial navigation. The observatory has the problem that we know exactly where we are. but we don't know exactly what time it is without making lots of star observations. At sea, it's the opposite problem. You know the correct time because you brought your clock to an observatory and they set it for you. Now you're out in the middle of the ocean, you've got no idea where you are, you work the problem backwards to get your latitude and longitude. Down in the basement, we've got all these telegraph wires connected to a bunch of gravity cells. These are batteries with claw's foot electrodes in the bottom of them. You'll notice the blue color. This is called blue vitriol, which is copper sulfate. At the beginning of the month, one of the astronomy assistants would mix up the blue vitriol and make the solution. And when you first make it, it has this intense Maxfield blue perish color. And as it starts to drain the battery and gets weaker, the color fades and fades. You can tell at a glance that the battery's dead just because it's not intense blue anymore. Each one of these would produce about 1 volt, 6 volts each, and that's plenty to send all the way across the city. So all these time signals come together in that hallway where we have this machine called a chronograph. This is a chart recorder where there's a pen mounted next to an electromagnet. You wind it up like a clock. There's a stack of weights underneath that slowly falls, and the drum rotates once a minute, and as it does, the pen leaves a spiral trace on the paper. I'll show you that in a minute. And when it gets a signal from one of the clocks, the electromagnet makes a mark. So you see this line, mark, the heartbeat of the clock every second. At the same time, you've got an astronomer looking through the telescope tapping a telegraph key. And that makes another mark on the paper, and you can measure where the observation of the star happened in relative to the clock. And you look up in a table to see whether the clock is running fast or slow with respect to the stars and make an adjustment to it. The first clock is the star time sidereal clock. This one was made by a company called Clemens Riefler in Germany. And you'll notice that it's underneath a bell jar, and it has this tank underneath it. And on the side, it looks like a bicycle pump, and it is actually a bicycle pump. What you do is you pump the bicycle pump, but instead of putting air in, you exhaust it. You suck some of the air out of it. And in later clocks, they would actually go down as far as you could. You didn't want the air resistance to disturb the pendulum. In this era, they couldn't go down to less than about 80% of an atmosphere. And that was because the oils that they used to lubricate the clock would evaporate, and you'd have bare metal running, and it would wear the clock out too fast. So the main goal here was not low pressure, but constant pressure. With clocks, you don't want anything in the environment to change. You don't want the temperature, the air pressure, the humidity, because all of that can affect the operation of the clock. And by keeping it sealed like this, first of all, inside of that massive clock vault, that insulates the temperature. The vessel surrounding the clock is a second layer of it, and then we control the pressure inside. Interesting aside is that once you wind the clock and set it into motion, you can't touch it because it's inside of the sealed jar. And you don't want to touch it because every time you do that, you disturb the time signals that people throughout Providence and other communities are relying on. So if you need to speed the clock up or slow it down a little bit, you use the bicycle pump. If you evacuate a little bit of air, there's less air resistance, it'll speed up by a very small amount. If you let a little air in, more air resistance, it'll slow down slightly. And you can control this very finely. So once you have the sidereal time on one clock, that's not too useful to you, because if I showed you what time it was sidereal, you'd be late for work tomorrow. We need to use a clock that is set to solar, civil time. And so a second clock in the vault has this contact switch. So each time the pendulum swings, it hits the switch, sends a telegraph pulse. And that's how we get the time out of the building and into the community. Interestingly, these scans are from the Providence Journal. And today you'd never see like a close-up photo of the inner workings of some machinery that's very obscure. They go into great detail in this article describing how the whole system worked, how many ohms of resistance are in the telegraph wire between the observatory and downtown Providence, and much more detail than you'd ever find in a popular newspaper today. So by 1893, the system was fully up and running. We were sending time signals continuously out of the building. There were two different wires. One of them went to the Rhode Island Electric Protective Company, which was located on Mathewson Street. If you've ever been to Cellar Stories Bookstore, that's the building I'm talking about. And they were basically a burglar alarm company. And many of their clients were banks and companies that repaired watches and clocks. They needed precise time so that they could check if the wristwatch or pocket watch that they were restoring and repairing was working correctly. And so the protective company had a burglar alarm so that their goods didn't get stolen, but during the daytime when it was open for business, they would use that same wire to send time signals from LAD to them, and they would use that for their calibrations. The second wire that we had went straight to City Hall, where the fire department was then located, up in the attic of the City Hall building, which is today the City Archives. And you can still see bits and pieces of the timekeeping system. There's a massive clock, wires that run through the attic to the various rooms. In a building like a courthouse or a city hall or a state house, exact time was important because of legal documents. So you have to pay a fine by 5 p.m. and if it's 5:01, you're going to get a fine on top of that. So from City Hall, the fire marshal would have a connection to all of the fire stations throughout the city. And at noon and 8:30 p.m., based on signals coming from LAD Observatory, it would sound some sort of a horn, a bell, or something in the towers of these stations. Part of the reason is a system check. Do the fire alarms work? You don't want to set them off all the time because people will be like, oh my God, there's something burning. But if you did it precisely like clockwork, people would come to expect that this was just a test of the system. But it was also a means where people in the community would be able to set their wristwatches and their clocks in their homes to exact time from LAD Observatory and know that it was correct. All of this is long before the era in which there's distribution of time by telephone or wireless. This is in the 1890s. Wireless radio was just an experimental phenomenon. It wasn't something that was commercialized yet. And so the standard time that we transmitted before, you might be wondering, what did we do before this? I was talking about a train crash in the 1850s. LAD Observatory didn't open until 1891. And in the meantime, we would get our time from other observatories by long-distance telegraph line. Mentioned here is Harvard and Yale. Typically, it was Ivy League institutions that had large observatories capable of doing this work. Also, the Naval Observatory in Washington, D.C. But Providence was very proud that we had our own timekeeping system here, and they mentioned this in the newspaper articles of the day. The arrangement, as now completed, allows almost no possibility for incorrect time. One of the things that they ran into was that if there was a blizzard or a hurricane, it would knock the telegraph wires down, and it could take days or even weeks to repair the damage, and so you'd be without accurate time during that. So having it localized makes a lot more sense. There's a saying that time is money. We know this to be true because we sold time. We were actually paid money to send time signals. When we first opened the observatory, it was $100 a year. That was a lot of money back then. By the time the system got fully up and functional, it was about $200 a year. In today's money, that would be roughly $5,000 a year. And so that would pay for the salaries of the assistants that did a lot of this work and made the observatory self-sustaining so that they could sort of subsidize the astronomical teaching and the public outreach. So now once you have this timekeeping system that's very precise, it wasn't just used for distributing time to the community, as important as that was. There were also a number of experiments that were conducted here. This is an invention by a man named Hezekiah Conant. He was the owner of the Conant Thread Factory, which at one time was the largest factory in the world that had the largest number of employees. It was located in Pawtucket. His hobby was designing precision clocks, and he was rather wealthy, so he could have the best clockmakers build his designs. This one has 4 pendulums. His idea was that if you had 2 pendulums and you took the average time of those, and you had another 2 and took the average of those, and then took the average of the 2 pairs, you'd get much better timekeeping than if just one pendulum, because there's less that can be disturbing the pendulums to prevent them from moving smoothly. In practice, it didn't really work out so well. Professor Winslow Upton, in his notebook, he tried for months to get this thing working, and it just wouldn't run properly. But it was an interesting idea, and each of the 4 dials at the bottom shows one pendulum, and then the top dial, the large one, shows the average time of the 4. Another thing that astronomers do is use timekeeping observations to measure where we are on the Earth. Now, if you want to measure the distance from, say, Greenwich, England to Washington, D.C., the way that they would do it in prior eras was you would load up a bunch of these marine chronometers, these precise clocks, you'd calibrate them at one end, put them onto a ship, send them across the ocean, and a month later they would arrive at the observatory. And then when you open them up, they'd all have different times, and you wouldn't know how far they had drifted. If it worked properly, you would be able to measure the difference in longitude between them. Remember that star map I showed you where I said that a particular star would be over, say, Providence at a particular time? Well, that same star would have been over the Greenwich Observatory many hours later. And so you can measure this difference between when one observatory saw the star and when the next one did, and determine the distance between them, the difference in longitude. Here's an experiment that was in 1905, the comparison of Washington and Ladd Observatory. So here we're going to the Naval Observatory in Washington, D.C. And the observatory astronomers got permission from the executives at the American Telegraph and Telephone Company, yes, AT&T, back when they used to make actual telegraph wires. And they got permission to use this long-distance communications line for scientific work, exclusively for an entire evening. And here in Winslow Upton's notebooks, we see he's a little nervous about the weather. Turned out it was clear. You don't want to go through all this trouble to set this up, and then it doesn't work. And this is an actual chart recorder from that chronograph that I showed you, where the pen is leaving a trace on the paper. Here we see 2 sets of signals. One of them is from Washington, and this is the solar time clock, which is transmitting to Providence. And then another set of signals offset a little bit, which is a sidereal clock here in Ladd Observatory. And the calculations on the side show the reduction of the numbers and the observations to figure out what the exact longitude difference is between the 2 cities. And when you transmit over long distances like Washington, D.C. to Providence, the signals travel fast at about 2/3 of the speed of light. But the signal gets weaker and weaker the further it goes from the source. And so you have to have this relay that's very sensitive. It pulls an electromagnet down, and there's a local battery connected to amplify the signal for the next hop. Well, when you insert this into the wire, there's a measurable amount of delay for the magnet to pull that down, and it's about 0.07 seconds, according to Frederick Slocum. So that's the delay, and most of the error is probably in that, because the system at Ladd Observatory would have been accurate to about 1/100th of a second during this era, which, by the way, is more accurate than any cell phone in this room. I've seen them off by as much as a half a minute or more. And now we're going to take a big leap. 1913 here. This is after the invention of wireless, the new technology. And Winslow Upton, again, describes a special wireless signal from Washington. Very interestingly, he says, received at Mr. Donnelly's house, and I'll talk about that in a moment. The numbers that you see, like 2299, that's the serial number of the clock. Each clock had a notebook, and every single calibration that you made was written down so that you knew exactly how much it had sped up or slowed down, all the work that had been done to it, and they would refer to the clocks by their serial number, which is stamped right into the metal dial. These are not the kind of clocks that you would have in your home, obviously. They're much more precise. So the experiment that was happening in 1913 was that in Paris they had a very precise clock in the observatory there. They ran a telegraph wire from that clock to a radio transmitter and then sent the signal across the ocean. They used a very interesting antenna arrangement, which is a bunch of wires hanging off of the Eiffel Tower. It was the only thing that was long enough for them to be able to string the long wires that they were using. So here we see a clock, and that's at the top left. The signal from the clock gets its energy from a battery, which goes to a relay, and then it goes into this radio transmitter and out through the antenna. Travels across the Atlantic Ocean and reaches another observatory in Washington, D.C., the U.S. Naval Observatory, which has a similar arrangement. And they exchange time signals, make comparisons of those observations of the stars to try to pin down that distance between the two locations. Meanwhile, here in Providence, Professor Winslow Upton is at Mr. Donnelly's house. Here's a photo looking towards the northwest, which shows the observatory that exists today. Way in the bottom right corner, right there, you can see that shed that I showed you earlier, where the astronomer was standing with the roll-off roof. And another shed has been constructed, which is right in front of it here. If you look really closely, I don't know if you can see it. I was wondering what that thin line was. It's not connected to the transit sheds. It looks like it's in the background. The Brown University Library scanned these giant 8x10 glass plates at ridiculously high resolution. So you can do one of those things like on CSI or NCIS where you zoom in. And I'm going to look at just that little part of the photograph right there. And here we see a rooftop on Observatory Ave, which has an inverted V amateur radio antenna, a ham radio antenna on top of it. One of our neighbors, this is very early, 1913, there were probably less than 150 ham radio operators in all of New England. By the 20s, there were only 150 or less here in Rhode Island. So it was quite rare to have a setup like this. I found in the Department of Commerce, Mr. Donnelly had a license to operate a ham radio as you needed at the time or today. His call sign for his station was 1UD, and he gives his address as Observatory Ave, right next to the observatory. During the census, I found out that his age when he was listening to these radio signals, time signals, he was 25 years old. He was living with his parents and his brother at this address, and he listed his occupation as a manufacturer of wireless apparatus. After World War I, he served in the military. He would later go on to become a pretty well-known radio engineer and had a large number of patents at the time. But even as a teenager, he built radio kits in his garage and sold them through magazines and earned a little bit of money that way. But here we have Harold P. Donnelly, 1913, 25 years old, and he's collaborating with a professor at Brown University on this international experiment. This is a very early example of what we might today call citizen science, where professional scientists collaborate with amateurs. You can almost imagine Winslow Upton at this time was very near the end of his life. Was an elderly man. And he goes over and knocks on the door of his next door neighbor and asks the neighbor's kid, "Can you program my TiVo? I want to listen to this program that's going to be playing." And the young man helps him out. And the results were satisfactory. They were able to get a pretty good measurement. Sadly, Professor Upton died before he could reduce the data. This postcard shows the apparatus that was in Washington, D.C., hooked up to the Naval Observatory. These are immense towers, almost the size of the Eiffel Tower itself, and there were 3 of them. The radio here in Providence on Observatory Ave would not have had the sensitivity to pick up something across the ocean. So the astronomers in Paris and D.C. would determine the longitude, and then Upton was listening to the difference between Washington and Providence, and he would get the offset from that and then calculate the offset to Paris. So I'd like to remind you that Ladd Observatory is open to the public today on Tuesday evenings when the weather permits. And I'd like to take some time to answer any questions that you might have. Yeah. Yeah, it's a little ambiguous on that. Dave asked how long we've been providing the timekeeping service. I've seen one mention that they continued doing it up until the time that Professor Charles Smiley retired in the early 1970s. But there's some caveats that go along with that. In the 1920s, early 30s, Professor Smiley wrote a paper where he says that, well, these time signals that we're getting by radio are just as accurate as doing the work itself. And so it's no longer necessary to go through all this trouble. But he did. He continued to train students and operate the system for many, many years. During World War II, he made a statement that if the enemy had attacked the U.S. Naval Observatory, Ladd Observatory would stand ready to provide time to the nation. And so the system was still working at that point. And I've seen calibration charts from as late as the 1960s where they were doing this work. It's hard to say because a lot of this just wasn't written down, but my impression is that this was part of training the students in the work and keeping the facility going. And it does provide some redundancy to have, I mean, there probably weren't very many observatories left at that point still doing timekeeping. Yes?
Other than Smiley and Upton, were there any other directors during that time period prior
Yes.
to 1970s?
Oh, in the early years there were. So Professor Upton came here, and when he started at Brown, several years before the observatory opened, they created an astronomy department, so he was the chair of the astronomy department. And then the observatory was constructed under his supervision, and he became the director. When he passed away, about 1914, there was some discussion about whether or not astronomy should get folded into the physics department or whether it should get folded into mathematics. There were 2 interim directors, they served briefly, who were mathematicians that were directors of the observatory. And then Professor Smiley became the director. He also was hired by Brown as a mathematician. We sometimes refer to Smiley as an astronomer, but technically speaking, if you were to get hired at Brown today, he would probably be in applied math. He was someone who used rigorous mathematical techniques to do things like calculate the orbits of planets, and a lot of that work continues here at Brown today. But he was here from, I think he first got involved in the late 1920s, and then he retired in the 1970s. Yes.
Surveys been going on. Apparently there was a burst of activity around the First World War associated with training people.
Well, interestingly, it happened before that.
Oh, okay.
Yeah. Let me just go back to that image here. So the little transit shed that was on Observatory Ave, that was built in the 1890s as sort of an interim while they continued working on the transit room.
The small building
This
there?
small one that's way up the edge behind this one. And then it wasn't needed after 1920. This one was built in 1907, and the main reason for it is that this transit room only has 2 stations, one for the scientific work, one for training students. And they started getting a lot of civil engineering students at Brown, and they were trained in surveying techniques, and they used the observatory to do their lab work. The lab work was very time-consuming, took many hours of observations with lots of students, and we just didn't have enough telescopes to go around. So this transit shed was actually built before World War I to train those students, and there were 5 observing stations in that could be used simultaneously. Then, when World War I started, yes, we did train in celestial navigation for the war effort, and that work presumably also continued during World War II.
And I've heard that the piers have been discovered now on the ground.
We found anomalies. When you look at the ground-penetrating radar, it has to be calibrated for each soil type. If it rained yesterday or was dry, that makes a difference. So you get reflections. Anytime there's a difference in soil material, for example, let's say the foundation presses down on the soil in a 1.5-foot wide and 10-foot strip. As you run the GPR back and forth across it, you'll see a distinct signature from that because the dielectric constant is different. We did see some massive things. Metal reflects radar quite well, and it bounces back and forth between the sensitive instrument and the underground object. We found what we think looks like a pipe, and it's not a horizontal pipe, it's vertical, and this could have been a pier that a telescope was sitting on. But it wasn't inside the transit shed, it was about 10 feet to the south of it. So this may have been just a portable location for setting up a telescope. We did find some very distinct signatures where I believe that the piers were, which are probably like concrete or something. It's very likely that you go to all this trouble to pour a massive amount of concrete into the ground. When you demolish the structure, you're not going to dig that up, you just bury it over. So we do hope to find something. And the archaeology of College Hill class that is taught here at Brown is looking into making this their project for next fall. Yeah.
Yeah, so towards sure, why not? Yeah, so towards the beginning of your talk, you mentioned that one of the really important reasons for keeping correct time was for purposes of trains not colliding with each other. I'm curious what some of the other complications were at the time where keeping correct time would be really, really beneficial.
Yeah, so by the time that Ladd Observatory opened, 2 of the main high-precision timekeeping tasks weren't really so much of an issue here. One of them is celestial navigation. So being a port city, we would have ships come in. But by the time that Ladd opened, Providence wasn't shipping so much on the ocean. Instead, it was coming in by train. At around this time that Ladd Observatory opened, the U.S. Naval Observatory started giving time signals for free to Western Union, which sent it out to all the railroads. And that kind of cut into the market. And there were all these economic things where the astronomers were really upset because they were using this income from the time signals that they were getting from the local companies to operate the observatory. So we never actually provided time signals for the railroads or for the navigation as much. It was mainly applications like Hope High School. You would have a master clock, and in every single classroom there would be a dial on the wall synchronized to Ladd, so that all the classes change at the same moment. A courtroom, for example, where there are multiple rooms with judges in them, they would all have the time synchronized to Ladd. And then the jewelers that repair the watches would also have that. Those were some of the main uses here in Providence. Also, we're getting into the the heyday of the Industrial Revolution, where you're punching a time card. And typically in a factory, not only would the time card be synchronized to LAD, but you would also have like a whistle for the change of the shift that would be triggered by the time signals. There's a little bit more to it too. Having precise time was seen as sort of a symbol of modernity, where this was sort of a matter of pride for the community that they had such a precise system. And there were also religious overtones too, like part of the Puritan work ethic, for example, where, you know, getting to work on time is a religious obligation. And so they may have gone to a greater deal than they needed to in order to have this precise time. But also having precise time at a university is important because, you know, the physics professors would come over and calibrate the stopwatches that they used for experiments, and, you know, you would need a much higher level of precision for that. The bell tower in University Hall was wired to LAD Observatory, and so we would ring the bell to change classes.
How long were time signals used?
Well, technically they're still used today. I mean,
That's my other question, because clocks are, there's an atomic clock now.
right, and I mean, let me just give you an example. The cell phone in your pocket. You've got a GPS on that. Also, each cell phone tower that you connect to has a GPS receiver in it, which picks up time signals from the orbiting satellites, which have atomic clocks in them. So when you turn your cell phone on, it handshakes with the cell phone tower, it gets the time from the satellite, sends it to your phone, and says, you got to update it a second. So, I mean, everything that I've described is still today, it's just invisible. It happens automatically. Yeah. But somebody out there, the U.S. Naval Observatory, NASA launching the rockets, I mean, we have to put all this infrastructure out there so that you don't see it. But it is still very much there.
And you had said that it's not completely accurate.
Yeah, there's a few reasons for that. One, they just don't care. I mean, it's not worth putting the effort into it to make it precise. Like, I have a special app on my cell phone that synchronizes to the server in my office, which has a GPS attached to it, and that's good to about a thousandth of a second. So if I need the correct time, I can get it on my cell phone. But for most people, you know, a professor's not going to, you know, say, hey, you're a millisecond late for class. As long as it's within a minute, you're probably good. But there are applications where this is critical. For example, today, navigation at sea, but also in airplanes. An airplane can use GPS to find out just how many meters you are off the ground. And that takes incredibly precise timekeeping because of the distance that light travels so quickly. It's about a nanosecond per meter, per foot. And so all this infrastructure, like aircraft, make use of precision timekeeping as the first step into getting their location.
But it's the same principle, though. It goes back to that.
Yeah, so we have ensembles of atomic clocks scattered around the world, and they're constantly comparing time with one another. The Bureau of Measurement in Paris, here in the United States, the National Institute for Science and Technology in Boulder, Colorado, and they maintain this ensemble of clocks that is more accurate than any single clock that people can build. And that is used to synchronize the satellites so that they can distribute it over the entire Earth. Yep.
So, a little later, but still towards the beginning.
Yes.
And I was curious as to what some of the,
So a couple of things. We use the transit telescope to measure what our exact latitude and longitude is. And if you solve that for a west point on the building and the main telescope is 20 feet to the east, well, you've already solved one of those things. So all of the telescopes are in the same line of latitude within like a centimeter or something like that. Yep. Yeah, and this is a skill that you have to be trained in. I kind of glossed over one thing, which was the telegraph key. So let's say we have two people observing through the telescope. I'm getting a little older, so my reaction time's a little slower. I get a young student who's used to playing video games rapidly, and their reaction time is going to be almost instantaneous. And there's going to be a big difference between the two of us in terms of the moment that our eye sees the star cross the thread, and then I push the button down with my finger. But that's not so much important because they have this process called the human equation. In a very real sense, the observer looking through the telescope is a part of this gigantic machine operating in the building. And they have to be calibrated just like the clocks. And so periodically you would have all the astronomers gather together, and they would all make observations one after another, and compare their measurements to one another. And it's like, okay, Mike's about 1 thousandths of a second slower than this other astronomer. And you would apply these corrections to every single observation they made. Now, in this case, we're recording it automatically. You can go way down below 1/10 of a second with this because the paper's moving fast, and you're getting these marks on the paper that are separated by like a centimeter or more. And you can use a ruler to measure it down to like a fraction of a millimeter. So that's a lot more accurate. Yes?
I have a question kind of related. In that picture of the telescope,
Yep.
the man is,
Oh, the very end?
yeah.
Yeah, so we don't use that system anymore. Instead, there's a shaft, which is right there, and this goes up to the gears. And at the bottom of the shaft, there's a ship's wheel that you turn. And there's two of them. One of them turns at east-west, the other north-south. And so you could just maneuver the telescope by turning that.
That must interfere somewhat with the telescope, must make it shake a little.
No, after you turn the wheels to move the telescope, you then turn a knob to like lock it down. So there's like a clutch that you release. So once it's locked into place, it's right on the star and it's going to stay there. They thought that this would be a good idea because instead of walking 5 feet over and turning the wheel and then going back to the eyepiece, you could just pull it from where you were sitting. It ended up not being that useful, I guess. And there are also slow motion controls, which are the little knobs near where his head is. And with that, the wheels will turn the telescope a huge amount, like 10 degrees. The wheels that are right next to the observer, you just turn those to like move the moon from here to here, just the width of the moon.
So
Oh, yeah, yeah.
So, I was curious as to, so you mentioned the,
Yep.
I was curious if there was some sort of,
So you want it to be an odd number so that you can take the average to get the center line. And you could use 7. 5 was considered a reasonable amount of error when you do the math and figure out, okay, if I have 5 separate measurements, what's my error bar? And it works out pretty good. In our telescope, it's actually a little bit more complicated than that, in that you just have 2 wires. But one of them you can move back and forth by turning a crank. And as you turn the crank, it follows, you keep it behind the star, and as it follows the star, every time it turns, it sends a telegraph pulse, and you can get 20 or 30 telegraph pulses out of it. So then you could take a very large number of averages, a large average. And that's a more precise way of doing it. No. I love questions.
I have an interesting cultural question, or something that I consider to be interesting.
Yeah.
Like full
Yep.
And so, it got me thinking.
So I think there's a couple of reasons. It would be harder for most things today, which are so much more complicated, to give that kind of a level of detail as part of it. And I think another big part of it is that people just don't care. I just want to turn my cell phone on, look at the time, and know that it's correct. I don't care how it works. There could be, gremlins inside my phone that are setting. So I think that's part of it. I mean, if people were curious about this sort of thing, you might read more about it. Jan?
I'd also like to say that there are other ways. So
Right. Although I should point out that during this era, these amateur radio operators, they would go to the local library, check out a book written by Marconi, which would have crude schematics in it, and they would build these things in their garage with like, I'm going to take a piece of broken light bulb, and I'm going to take a nickel. I need some nickels, so I'm going to shave some shavings off it, and they would just build these things. There was much more of a do-it-yourself kind of attitude during this era. And so I think that some of the details in the newspaper article would have appealed to people who were hobbyists who did this sort of thing.
it's also really striking how many fewer reporters were.
A cool cake, too. And one last thing I'll mention is that, up here on the screen, I've got the web address for our blog, and I've got a lot more stories about the history of the observatory if you want to read that at that website.